This conference will now be recorded.
Hello dear students, we are continuing the discussions on various type of questions related to different topics in electrostatics. So today we have picked up different questions from the topics electrical energy, that means electrostatic energy, then motion of charged particle in electric field and electric dipole. So these three topics, on these three topics we have collected few questions. So we'll be discussing these questions and this will help you to build your concept. Okay, so let us start our discussions with this question shown in the screen. So the first question says choose the incorrect statement. First statement says the potential energy per unit positive charge in an electric field at some point is called the electric potential. That is very true. Okay, so potential energy per unit positive charge, it is very true. Okay, so if suppose I have capital Q charge and I have to find out potential due to this capital Q charge at a distance r, okay, at this particular position P. So what I should do, I should actually calculate the potential in this, like the way we do. So suppose a unit positive charge, okay, unit positive charge, some suppose +1 coulomb is brought from infinity, okay, some infinity distance, okay, infinity to this particular position. So to do that, how much work we have to do? Okay, so that work will be stored as, you say, potential energy per unit charge or simply potential. Okay, that is the thing. So this is correct. So we have to find out the incorrect statement among these four. The second one is says, see, this is saying that the work required to be done to move a point charge from one point to another in an electric field depends on the position of the points. This is also true actually. So work done does not depend on, see, for electrostatic case, work done does not depend on path. Okay, it does not depend on path, it depends on the final positions, or like positions. It depends on the position. It is true actually. Depends on the position. Positions. Okay. The potential energy of the system will increase if the positive charge is moved against the Coulombian force. This is also true. So these are all true. Let us see the third option. The value of fundamental charge is not equivalent to the electronic charge. No, this is actually true only. This is not. This is actually incorrect. True in the sense, I want to say that fundamental charge is taken equivalent to one electronic charge, or simply E. Okay, and that has got a value positive 1.6 into 10 to the power minus 19 coulomb. Okay, so this is the fundamental charge. So the fourth option is not actually correct. So we have got the correct answer by this, the fourth option. Okay, let us go to the next problem. Okay, so this is also a very interesting problem. You see, this problem says in the electric field of charge q, see this is charge q, positive charge, another charge is carried from a to b, say a to b or a to c, a to d or a to e. The question is, then work done will be minimum along AB path, minimum along AD path, minimum along AE path, zero along each path. So among these four, which one is the correct answer? See, I'll tell you one thing. When I have a positive point charge, okay, at an equal distance, so if I take r distance and if I draw a sphere around it, around this positive charge, I think this is not exactly at the center. Let me draw the sphere itself. Sorry. Okay, just take this as a representative figure. Suppose positive q is kept here at the center. So it will actually produce potential, equal potential at each point on the surface. Equal potential. That means, this point charge will create an equipotential surface, or I can say concentric equipotential surfaces like this. Concentric equipotential surfaces. Now you see in this figure, this A, B, C, D all are on the surface of the same sphere. See, I have potential difference between this point. Suppose if this is A and this is C or B, let us say. So these 2 points will have potential difference, but any point on the same surface of the sphere, they will not have any potential difference because they are sitting on the equipotential surface that is created by the point charge. You might be thinking, how is it producing equipotential surface around it? Let me tell you. See, the potential for a point charge at any distance r is given by 4 pi q by 4 pi epsilon naught r, right? So this term is constant. Okay, this term is constant. See, this has only r dependence, and whatever point you take on the sphere, this r is same for all the points on the sphere from the center, isn't it? So therefore this A, B, C, I'll tell you, A, B, C, D all are lying on the surface, okay, on the equipotential surface, I should say, on the equipotential surface. Equipotential surface. So therefore there is no work done when I bring a charge from one point to another. Okay, if I have these 2 points A and C, I bring a unit positive charge or any other charge from A to C, my work done should be like this. See, AC will be Q into potential difference, okay, VAC. If this potential difference VAC means VA minus VC or vice versa. If these two are equal, then there is no difference, right? If this is 0, then what is the work done? Work done will be 0 for moving a charge from one point to another point. You don't have to do any work. So fourth option will be the correct answer for this question. Now, this is an interesting question. See, a charge 10 ESU is placed at a distance 2 centimeter from a charge 40 ESU. Okay, let me just tell you what it is saying. Suppose this is 10 ESU, positive 10 ESU. It is somewhere here. Now, at a distance 2 centimeter from the charge 40 ESU. Okay. So this is suppose 2 centimeter. And this is 40 ESU. 40 ESU charge. And with a positive sign. From another charge minus Q, it is, and 4 centimeter from another charge of minus 20 ESU. So this is minus 20 ESU. Okay. And this is, this is 4 centimeter. So what is the potential energy of the charge 10 ESU in arcs? So this is simply, see, the total potential energy U, total potential energy U of 10 ESU charge will be obtained as Q1 V1 plus Q2 V2, like that. Okay, I can write in this way. Okay, sorry, this Q1 itself, so like this. Let us write this Q. That means, this is Q, the charge 10 ESU, and the potential created by 40 ESU at this particular position. That means, potential at 10 created by 40 ESU plus potential at 10, or at the place of 10, created by minus 20 ESU. So this is how I can write. Now look, what is this? What is this 10 to 10 40? That means potential. So I can write K Q, that is here 40 ESU. I'm just trying to find out the potential. So 40 ESU divided by the distance 2 centimeter. So in this case, you should remember that in CGS unit, K has got value 1. So this has got value 1. Okay, in CGS unit, K has value 1. That means, this is ESU by centimeter. So we can actually go for this as 20 ESU by centimeter. And for this, the other one, 10 minus 20. So this is, you will get with minus sign over here, 20 divided by 4. So you will get minus 5 over here with the same unit. Now let us do things here. 10 ESU, and here it is C, B it is 20, and here it is 5. So this will be in ARG actually, ERGS. So it will be actually 150 ERGS args. Option 3 will be the correct answer for this question. Okay, so let us go to the next problem. Okay, so what is this question saying? As shown in the figure, on bringing a charge capital Q, positive charge, from a point A to B, see A to B, and from B to C, work done are respectively 2 joules and minus 3 joules. Now you have to find out work done in bringing the charge from C to A. This is very interesting problem. So the question says work done along this path in bringing a point charge capital Q is 2 joule. Okay, and then work done along BC path minus 3 joule. You have to find out what is the work done when it is bring from C to A. This is the work done. So what is the principle you are going to use here, or what concept you are trying to use here? That is the conservative nature of the force, electrostatic force. So when a force is conservative, then work done along closed path, along a closed path is 0. So this is the concept here. Work done along any closed path due to electrostatic force will be 0, because electrostatic force is a conservative force. So electrostatic force is a conservative force. Conservative force. Okay, so now according to this thing, what we can write? We can write AB plus WBC plus WCA is equal to 0. Now see, these two are given, so I can write WCA is equal to minus of WAB plus minus of WBC. I'm sorry. Oh, did I erase everything? Okay, we'll write once again. WAB plus WBC plus WCA. This has to be 0. Now WCA I have to find out. I have to find out WCA. So this is equal to minus WAB minus WBC. Now what is WAB? That is given as this one, 2 joule. So minus of 2 joule minus of minus 3 joule here. That means 3 minus 2 joule, or this is 1 joule. Okay, with a positive sign obviously. So the option 2 will be the correct answer for this question. Okay, so let us go to the next problem. Yeah, this is also very interesting problem. The question says a 5 coulomb charge experiences a force of 2000 Newton when moved between 2 points along field along the field separated by a distance 2 centimeter in a uniform electric field. So you have uniform electric field over here like this. So if a charge of 5 coulomb, say, that is moved from some point A to suppose some point B, is moved, and during this it is experiencing a force of how much? 2000 Newton. And this AB distance is actually, let us say DAB distance is given by 2 centimeter or 2 into 10 to the power minus 2 meter in a uniform magnetic field. So you have to find out what is the potential difference. See, when it is experiencing a force along the direction of field and we are moving it from a particular point, one point to another, then there will be obviously work done by the external agency, which is bringing the charge from A to B. Okay, so you know, the according to the definition of the potential energy, we can write Q into VAB, the potential difference, that is actually the work done, and that is there 200 Newton into 2 into 10 to the power minus 2 Newton meter. So this is actually the work done. Here Q is given, so I can find out VAB is equal to, see, this will cancel each other, so this will be 40, and you have 5 coulomb over here. So this is joule per coulomb. Okay, joule per coulomb will be actually volt. So 8 volts. Okay, 8 volts. So the first option will be the correct answer for this question. All right, so let us go to the next problem. What is this problem saying? This problem says, when the separation between two charges is increased, the electric potential energy of the system, the electrostatic potential energy or electrical potential energy, that has got an expression Q1 Q2 by, if I write K by R. Okay, that means, you know, somehow this is varying as 1 by R. So electric potential energy is varying as 1 by R. Obviously this will decrease. If the separation increases between the charges, so this is actually small r is separation between the charges. Okay, so it will decrease. Now this question says an electron and proton are set free in a uniform electric field. The ratio of their acceleration. That means, you know, there is a uniform electric field, say sorry. This is uniform electric field, so there an electron has been set free. So what will be the acceleration in this electron? So first of all, if the electric field lines are like this way, so electric field also will be in this way, and the force experienced by the electron will be minus q into E. That means this negative force means it is actually the electric field is actually supplying retardation to the electron. So what is the value of that retardation? That will be F by m. This will give you the acceleration. So here F is my QE, this is m. So QE by m. So for one electron and one proton, they have eventually the same charge, but they don't have the same mass. Okay, so acceleration of electron and acceleration of proton is actually so if you take the ratio, so this is mp by ma me. mp by ma, so option 3 will be the correct answer for this question. Okay, this is another interesting problem. What is this problem saying? The problem says an electron enters an electric field with its velocity in the direction of electric field lines. Okay, look, there is uniform electric field over here, say, and the direction of electric field is this. Now an electron enters an electric field with its velocity, some velocity it is entering, okay, some velocity ve. So see, this is the direction of electric field, and see, in the same direction electron is moving. We know that the force that electron experiences due to the electric field present over here is minus E into E, minus E into E. Capital E is the magnitude of the electric field or strength of the electric field. Now this means what? It is giving some negative acceleration or some retardation to the velocity of the body. So this electron was having initial speed or initial velocity, but when it enters in the region along and starts moving in the same direction as the electric field will actually provide one retardation to the electron. And as you know, if you apply retardation, the velocity of the electron will decrease just after entry. So option 3 will be the correct answer for this question. Okay, so let us see the other options. The first is saying that the path of electron will be a circle. Say in case of electric field, you know, when there is an electric field, suppose this way, a uniform electric field, and we are like a charge is moving, positive charge is moving this way, so that will actually eventually move like this. So this is kind of a parabola. Okay, we'll go to the next problem. So what is this problem saying? This problem is saying that a particle of mass m and charge q is released from rest in an electric field E. Then kinetic energy after time t. A particle of mass m, charge q is released from rest. Okay. Then say suppose this is the uniform electric field E. So the question is, what is the kinetic energy after time t? So what is the kinetic energy after time t? So what we have to do, I have a charge. So force on the charge particle will be q into the electric field. So I'll have some acceleration because it is positive charge. So q e by m. Now if I have a particle which is just released without any initial velocity, after time t, suppose it has reached here, so it will attain certain velocity because the particle is moving with a constant acceleration, and that acceleration is q e by m, q into e by m. So now this problem is actually has become problem of kinematics. We have to find out what is the velocity after time t, so that is u plus at. So v, so u is equal to 0, therefore what I can write, v is equal to at. So we have got the velocity after time t. So what will be the kinetic energy? Half m v square, half m v square. V is 80 whole square. Okay, now let me put the values. So m t square, a is qe, so let me write q square e square by 2 into m square. So this will cancel each other, and I will get kinetic energy e square q square t square, e square q square t square by 2m. So this is the answer. So option 2 will be the correct answer for this question. Okay. Now we'll go to the next problem. Okay. So this problem says a charge q is projected into a uniform electric field E. The work done when it suffers displacement y along the field direction. Question is like this. This is the uniform electric field. A charge particle is projected in uniform electric field. The work done when it suffers a displacement y. So this is simple actually. Work done will be just F into Y. Force into Y. So what is force here? Q into E. That is the force into the displacement. So this is the work done. Okay, so option 1 will be the correct answer for this question. Now this is another interesting thing. Let us try to understand and solve it. The question says, figure shows below the path of positive charge particle 1 through a rectangular region of uniform electric field as shown in the figure. That means, you know, the inside this region there is some uniform electric field. We don't know the direction of the uniform electric field here. Okay, we don't know the direction of the electric field initially, but when we keep one unit positive charge, it will have a parabolic path like this. That means what? That means the charge particle is always pushed in this direction. That means electric field is in this direction. Okay, so the positive charge is moving in this way, means electric field has got direction this way. All right, we have got the direction of electric field. Then see, for this negative charge, what will be the, like, in which direction it will go, whether it will go down, up. Okay, I think there are many options. Let us just find out. So this negative charge 2, so 2, 3 and 4, where will they go? Down, up, like top, bottom, etc. So here, look, this one is negative charge and electric field is along that direction. So this will move, actually move down like this. So charge 2 will be moving down. What about 3? 3 has got positive charge, so it will move up like this itself. Now what is the charge? Charge is in, charge, okay, charge of positive, fourth charge is negative, so it will go down like this. So first I have to go down, then this has got upward, okay, and 4 again down. Okay, this will be the answer actually. See, if I write, so this will be, so it will be actually 2, I have to take it to bottom or down. So 2 is down, ball 3 is up or top. Option 4. 4 says it is also down. So down, top, down. Okay, so this was the question. Now let us go to the next problem. Okay, so this is very interesting problem. This is from dipole. When an electric dipole P is kept in a uniform electric field E, then for what value of the angle between P and E will the torque be maximum? See, we know the expression for the torque. due to dipole as P cross E. P cross E, or this will be P E sine of theta. Now P means, suppose the dipole length, positive charge and negative charges are separated by 2D. So 2 into Q into D E sine theta. Sine theta. Now in this case, to get the maximum torque, this has to be 1, or theta has to be 90 degree. Okay, so for maximum torque, will be for 90 degree. Okay, now we'll go to the next problem. For a dipole, the value of each charge is positive, negative. So dipole, they both have 10 to the power minus 10 ESU stat coulomb, and their separation is 1 centimeter. Sorry, 1 angstrom. Okay, separation between them is 1 angstrom. So then what is the dipole moment? Dipole moment will know Q into, sorry, so dipole moment P is Q into the distance between them, or separation between them, that is minus this centimeter. Okay, so this is becoming, so this much stat coulomb into centimeter, and 1, see, 10 to the power minus stat coulomb, 10 to the minus stat coulomb is equal to 1 d by, this is the unit itself. So 10 to the power minus 18 stat coulomb is equal to 1 d by, that is this one. Now this question is very straightforward. If you know the result, you will be able to answer. What will be the ratio of electric field and electric field at a point on the axis and an equidistant point on the equatorial? That means, you know, this, see, the question is said that we have to find out the ratio. So suppose they are, okay, let me draw. Okay, so This is suppose the perpendicular bisector, and on the axis there are poles. Okay, like electric field. So electric field at any axial point will be actually given by this is 2p actually. Okay, and for equatorial plane, this kind of plane, it will be p with a minus sign, 4 pi epsilon naught. Okay, so what I'm trying to say, the electric field at axial point and on the equatorial plane has got a ratio 2:1 actually. If you know electric field at axial point, electric field at axial I have written equatorial. Okay, so I'll just tell you one more point. Okay, this is 2:1. So at the equatorial plane there will be field, but there will be no potential. That is what I just wanted to say. Now I think this is the last problem for this session. We'll discuss this question and finish the session for today. See, this question says two particles, each of mass m, attached to the two ends of massless rigid non-conducting rod. So this is a rod, and there are two masses of equal. Okay, both are equal masses on either side, say, and it has got a length L. Two particles carry positive q, negative q respectively. Then the arrangement is held in a region of uniform. This arrangement is held inside electric field of uniform, like in a region of uniform electric field E, such that the rod makes an angle theta. Which this theta is very small angle with the field direction. Then you have to find out what is the time period. So how do you do that? See, I'll just go to the next page. So suppose I have a dipole here. Actually, there are two charges, positive and negative. See these two charges. These particles have positive and negative charge. So that means, you know, this rod will be massless rod, will act as dipole. So here suppose positive charge and here negative charge is there. Now you are in the uniform electric field where the electric field is making an angle theta for the dipole. Okay, this is the dipole. This is positive charge over here. Okay, sorry. Positive charge here, negative charge. Now you have to find out what is the time period if this is kept like this, and suppose given a slight displacement delta theta, then it will actually oscillate like this. Okay, it will oscillate like this. So oscillation of this will have certain period that we have to find out. We know here tau torque is equal to PE sine of theta, and that can be written as this theta can be written as Sin theta can be written as theta itself as sin theta. Theta is very, very small angle. Now we know again tau is equal to I alpha. Alpha is the angular or rotational acceleration. So I have to find out frequency of oscillation for this. So this PE actually I can write, this is length is L actually, right? So I can write Q into L into E sine of theta. Okay, I'm sorry, sine theta I should not write further. So this is Q into L, E and theta. See now this can be written as I alpha is equal to Q L E theta. Okay, now what is alpha? Alpha is Q E L theta by I. So this is so far it is fine. See, this is kind of oscillatory motion. So acceleration, see we know acceleration is minus omega square x, omega square. This is the condition for simple harmonic oscillation. Okay, so here so if I compare with this two, then what I get? So if we compare this, we'll get actually omega square will be QL so QL E theta EL by this has got. Okay, so once I get acceleration, then what? Okay, by the way, what is I will be actually m1 r1 square plus m2 r2 square. So m1 r1 square, m2 r2 square. See r here actually L by 2. That means it will be actually, so this distance are same, mass is the same. So m L by 2 whole square actually. That means into 2. Then m L by 2. Okay. Here with the square here. M L square by 2. Now if we put all this here, now we have to find out what is, okay, omega I have got here. Q into E into L by I is actually, so 2 will go there and here it will be m square. Okay, let me just write it here itself. This concept I'll erase. So time period is equal to 2 pi by omega. omega is okay, so this is ml square divided by q v ml square by 2, so 2 should come here, q e e l, I'm sorry, this should be here. So 1L cancel each other. So 2 pi square root of see the options. So 2 pi ml by 2 q e. I'm sorry, this L will not be here. 2 q e, and in the numerator there will be ml square root. So 2 pi ml square root of ml by 2 q e. So this first option will be the correct answer for this question. Okay, so this is the time period. For this, I'll stop it here for today. We'll have similar kind of sessions for class 11 also. We have already started with kinematics, so we'll continue with the kinematics, taking many problems to strengthen our concept. Okay, so thank you for your patience. Bye for today.